In this section, we discussed the nonlinear current-voltage relationship of a diode made from a p-n junction, which can act as a check valve for electrical current, allowing current to flow one way but not the other. High-power diodes and switches are needed for the rapidly growing power electronics industry as we move to electric vehicles. We saw that in equilibrium, the hole and electron concentrations change drastically from the p to the n region, and that this change is primarily in the space charge layer where an internal voltage of V0 is established. We found that the relationship between the minority hole or electron concentration is simply an exponential of the built-in potential over kT. The exponential gives the ratio of the charge carrier concentration in two regions. This is like a Boltzmann distribution function for two different states, where the minority concentration is like a fraction of the thermally excited particles that can get over the barrier of potential EV0. Now let's consider the case where a voltage bias is applied across the junction. The voltage applied puts the system out of equilibrium and a net current will flow. Since there are plenty of charge carriers in the neutral p-type and n-type regions, a current can flow with very little voltage drop. So most of the voltage drop is then across the space charge layer where the built-in voltage is. Let's start with the case that V opposes V0. V is driving electrons and holes towards the junction, which we call forward bias. V reduces the barrier voltage in the space charge layer. So we would expect that the minority charge carrier concentration just on the other side of the space charge region to be higher, as if more charge carriers can cross the barrier due to thermal excitation. Knowing that the barrier is reduced by V, we can expect that the concentration at the edge of the space charge layer, x equals 0, to be given by an adjusted exponential. Recognizing that the V0 term can be pulled out, and that it is simply the minority carrier concentration with zero bias, we find the relationship that is often called the law of the junction. The extra minority charge carriers, compared to the concentration that is there for zero bias, are called the injected minority carriers and given by the exponential -1. Notice that under zero bias, V equals 0, the excess or injected minority concentration is 0. This excess concentration should decrease as we look deeper into the neutral semiconductor, decreasing until the equilibrium value is reached, which is determined by the dopant concentration in the bulk. We can expect that this is due to charge carrier diffusion and that the decrease should be an exponential decay where the characteristic length is the diffusion length of the minority carrier. For the device, we want to know the total electrical current due to the bias voltage. The total current is the sum of the electron and hole, diffusion, and drift currents. As we can see in the sketch, the current profile looks quite complicated because the excess minority carriers are recombining, changing the concentrations and also the individual currents. But notice the total current is a simple constant. It is constant because under steady-state conditions, the total electrical current needs to be conserved, Kirchhoff's current law. So to estimate the total current, we really only need to know the current at one point. We will calculate it only at the edge of the space charge layer where we know the minority carrier concentrations. In the neutral regions, the current due to the minority carriers is primarily from diffusion, which we can calculate from the diffusion equation. Since we know the concentration profile is an exponential due to the excess injected charge carriers recombining, the diffusion current at the edge of the space charge layer is simply this derivative, which depends on the diffusion coefficient and the recombination time of holes, and also the equilibrium minority carrier concentration and this exponential of the bias voltage. We then use the same argument to find the electron minority carrier diffusion current at the outer edge of the space charge layer. Then, noticing that the electron and hole currents don't change much in the thin space charge layer, we finally get the total current by adding the electron and hole minority diffusion currents in the space charge layer. The current across a p-n junction we just derived is a form of the Shockley diode equation. Recall that a simple resistor has a linear IV characteristic, where a change in bias voltage produces a proportional change in current. If we plot the current I that results from a voltage V, we get a straight line with slope 1 over resistance. At zero bias, there is no current, which is a result of the device not providing any power. Current flows as easily in the reverse as forward direction. The IV curve is symmetric. The simple PN junction diode is also a passive device that doesn't produce power, or at least under equilibrium conditions of constant temperature and no illumination. Under zero bias, or V equals 0, the resulting current is 0. However, when a positive voltage is applied, the current increases exponentially. On a linear scale, the current seems insignificant until a particular voltage is reached, and then it rises rapidly like hitting a knee in a curve. We call this forward bias. If the opposite voltage is applied, the current in the direction of the reversed voltage is very small, usually too small to run a device. For most of this reverse bias, the current is essentially I0, called the reverse saturation current. Thus, a diode effectively only allows current to flow in the forward but not backward direction. The PN junction breaks the symmetry of a simple conductor. In a circuit diagram, a diode looks like an arrow indicating the direction of positive current flow. If voltage is applied in the reverse direction, it acts like a very large resistance. Diodes in a circuit can be easily confused as resistors, but typically only have one band indicating the direction of forward bias current flow. A diode acts like a one-way valve, only allowing current to flow forward but not backward. When a battery is connected to a diode in series with a light bulb in forward bias, there is some voltage loss, about 0.7 volts, but otherwise the diode allows the current to flow and the light to turn on. However, when the battery is reversed and the diode is in reverse bias, it doesn't let enough current to flow to the light bulb. It acts like a large resistance of about 10 megaohms. The diode is acting like a hydraulic check valve, allowing flow in one direction but not the other. This is because under forward bias, the electrons and holes are pushed together, reducing the depletion region and the barrier for charge to flow. While in reverse bias, the charges are pulled apart, with depletion region even increased from an equilibrium value. If the bias is an alternating plus and minus AC signal, the diode lets only one direction of current through, effectively outputting 0 when the bias is in the other direction. This results in a rectification of the AC voltage such that only positive voltage is output, which can then be used to power a DC circuit. There are a number of materials properties that affect a diode's performance, where material selection and engineering may become important in device design. We saw that in the diode equation, the materials parameters are in the reverse saturation current, J0. This was derived from the sum of the electron and hole minority diffusion currents, where each depend on the diffusion coefficient D, minority carrier lifetime tau, and the dopant concentration, which came from the mass action law. The intrinsic N brings in the band gap, which makes the exponential under forward bias look like EV minus EG, meaning that the diodes for semiconductors with larger band gaps, such as gallium arsenide or silicon carbide, have a higher turn-on voltage than germanium or silicon diodes. But they are also less sensitive to temperature. Silicon carbide electronics are rapidly being developed for power conversion, such as electric vehicles, because they run much hotter and are much more efficient than silicon devices. The other material parameters for both electrons and holes that are important, but not in the exponential, in addition to the minority carrier lifetime tau, are the mobility through the diffusivity and Einstein relation, and the effective mass through the effective density of states of the conduction and valence bands.